A box of cereal, specifically Lucky Charms, starts from rest and slides down a ramp inclined at 30 degrees above the horizontal. The coefficient of kinetic friction is 0.3. The length of the ramp is 1.5 meters. A. What is the acceleration of the Lucky Charm box? And B. What is the speed of the cereal box when it gets to the bottom?
Draw a picture!
Alright, our first step is to draw a picture. We have an inclined plane, and we have a box of Lucky Charms sliding down it. Just like the last problem, I'm going to tilt my x and y axis so that the x-axis is parallel to the plane. So if I draw my axes in the corner over here, my x-axis and my y-axis is perpendicular to the plane. Well, that's just a reminder for me.
Alright, 2. Label your nose. Your knowns. Label your knowns.
We go back to the problem, we see that the box starts from rest. So I'm going to say that V naught equals 0 meters per second. All right, and that's key to extract that from the problem.
So if a problem says that something starts from rest, it's super important to understand that that means that the starting speed is 0 meters per second.
We know that the ramp is angled at 30 degrees above the horizontal, so that means that this angle here, let's call it theta, is equal to 30 degrees. The length of the ramp is 1.5 meters, and when we're talking about the length of the ramp, we are talking about the longest side of the ramp.
Or the hypotenuse.
The side that the box slides down. So that entire length, I'm going to call it x, is equal to 1.5 meters. All right, so we do have friction in this problem.
And I know you're like, frick, I don't want to deal with friction, but that wouldn't be a very efficient way of teaching you how to solve inclined plane problems if we didn't put friction in them.
So we know that the coefficient of kinetic friction is 0.3. So I'm going to write that over here. Mu k equals 0.3. Alright, so we know that in this problem, because the block slides down, it was able to overcome the coefficient of static friction and start accelerating down the plane.
If static friction was strong enough, it would prevent it from sliding down the plane. So just keep that in mind for future problems.
We have everything that we know, however, it's key that we draw a free body diagram to help us. Alright, so this block is on Earth, so therefore the force of gravity is acting on it. And even though we tilted our axes, we know that the force of gravity still points downwards toward Earth. So that force of gravity still needs to point directly down. I'm going to give it a label FG. Remember, just because we tilted our axes, that does not affect the direction of the force of gravity. It's still going to act downwards. Okay, because we are on an inclined plane, we want to split the force of gravity into its vertical and horizontal components. And so I'm going to draw the all-famous triangle with my vertical component being perpendicular to the plane. That is FGY, because that is aligned with our y-axis, which is now perpendicular to the plane. And we have FGX, which is parallel to the plane.
If this is confusing, watch the video with the inclined plane problem where there is no friction. I explain why and how to split gravity into its components.
By splitting the force of gravity into its components, we are not changing the force of gravity, we are just looking at it in a different way. The effects that the vertical and horizontal components of gravity have on the motion of the block are the same as the effects of the actual force of gravity, this green arrow that we've drawn down. So I could cover up the green arrow and look at gravity in terms of its components, or you can cover up what we've just drawn and you can look at gravity that way. But in order to solve this problem, you do want to look at it in terms of its components. So what other forces are acting on this? Well, the block is on a plane. The block is pushing down on the plane, so the plane pushes back with a normal force. And the normal force is perpendicular to the plane, so it is going to be perpendicular to the plane. and that is my normal force, F sub n. All right, and finally, in this case, we do have friction. Friction always opposes motion, and because the block is moving downwards on the plane, first of all, we know it's going to be kinetic friction because the block is moving, and friction is going to be pointed in the opposite direction to the motion of the block. So if the block moves this way, friction is going to point in the opposite direction parallel to the plane because the block is also moving parallel to the plane. And so this is my force of friction that way. Now I've labeled everything that I know. What is our target? Well, part A is asking us, what is the acceleration of the Lucky Charms box? So I'm going to write my target, our acceleration, and it is in the x direction because our x-axis is parallel to the plane,
and the block is speeding up parallel to the plane, which means that the acceleration is parallel to the plane. Specifically, the acceleration is positive because the block is speeding up in the direction of the positive x-axis, which means the acceleration is positive and also in the direction of the positive x-axis. There is no a sub y, or vertical acceleration, because the y-axis is perpendicular to the plane and the block is not changing its speed perpendicular to the plane, which means there is no acceleration perpendicular to the plane.
So this is our target. Now we have set up the problem. It's time to find an equation. The equation has to have the variable that we're looking for, or the acceleration in this case. And the rest of the variables in the equation we should know already. We have some forces, we have an acceleration. We don't have a mass, but remember I said the mass might possibly get canceled out. And we do have an inclined plane problem, so my first thought is to use Newton's second law. That should always be your go-to when you're talking about an inclined plane. Hopefully this isn't Newton to you. So Newton's second law, we are talking about the acceleration in the x direction. So I'm going to write Newton's second law as the net force in the x direction equals the mass times the acceleration in the x direction. Remember, this direction here, the direction that the block is accelerating, is our positive x-axis. So when we're talking about our net force, we're talking about forces acting along the x-axis or parallel to the plane. Well,
we have the horizontal component of gravity
accelerating the blocks down the plane. The vertical component of gravity does not accelerate the blocks down the plane because it is acting perpendicular to the plane. Okay, so our force of gravity in the x direction is part of our net force, and it is positive because it is acting down the plane, accelerating it down the plane.
And down the plane is in the direction of our positive x-axis.
The normal force doesn't cause any acceleration. It's acting perpendicular to the plane or along the y-axis, so we don't care about that right now. And finally, we have the force of friction, which is definitely acting parallel to the plane, however, in the opposite direction to the acceleration. The force of friction is resisting the block's motion, and so we are going to subtract it from the force of gravity.
The reason friction is negative is because it is acting up the plane, which is the direction of our negative x-axis. If down the plane is the positive direction, then up the plane is the negative direction, which you can see by the axes we drew at the beginning.
All right, there are no other forces acting along the plane, so that is equal to the mass times the acceleration in the x direction. Next step is to isolate my variable, so I'm going to divide by the mass and say that the acceleration is equal to the force of gravity in the x direction minus the force of friction divided by the mass. Now I'm going to replace this force of gravity and force of friction with variables that we know. Okay, hopefully we know that the force of gravity is equal to mg, okay? Total force of gravity. Now, we want to find the component of the force of gravity. And so if you remember from the previous problem, the angle here, theta, between this purple and this green arrow is equal to the angle of the inclined plane. And so because we know the angle and we know the force of gravity, we can find the component of the force of gravity using some triangle math or trigonometry. Now don't triangle too hard on this. All you have to realize is that because we're looking for this side of the triangle and it's opposite to the angle, we have to multiply by the sine of the angle. So our force of gravity in the x direction, the horizontal component, is equal to Fg sine theta. And now we are subtracting the force of friction. Now if you look at the formula for the force of friction, it is equal to the normal force times the coefficient of friction. And this is kinetic friction because the block is moving. We can break this down even further. I don't like this mass here. I don't like it. I want to get rid of it. And so I'm breaking everything down into its components so that maybe I can cancel all the masses out. That's my end goal. So I can rewrite Fg as mg, because remember, force of gravity equals mass times acceleration due to gravity. So mg sine theta minus, let's talk about the normal force. This is super key. This is probably the most challenging part of the problem. If we look back at our picture,
the box is not accelerating along the y-axis or perpendicular to the plane. The box is only accelerating along the x-axis or down the plane.
So that means that the net force in this direction or along the y-axis or perpendicular to the plane is 0. The net force perpendicular to the plane is 0, which means that the normal force acting perpendicular to the plane has to cancel out with the only other force acting perpendicular to the plane, or the vertical component of gravity.
Because if we have 0 acceleration perpendicular to the plane, then the net force perpendicular to the plane must be equal to 0.
Which means that the magnitude of the normal force is equal to the magnitude of the vertical component of gravity. They act in opposite directions and cancel each other out. I can replace the normal force with the vertical component of gravity. So I'm going to write that over here, just kind of a star mark, that the normal force is equal to the vertical component of gravity. So in our equation, I'm going to rewrite normal force as the vertical component of gravity. If I go over to my triangle, I need to find the purple arrow, and because the purple arrow is the side close to the angle, the close side, I'm going to use cosine. So my vertical component of gravity is equal to Fg cosine theta. So this here is my normal force. Okay? And don't forget the coefficient of friction. All over mass. Okay? I'm really close. I'm almost done with breaking this down. The only thing I need to do is rewrite the force of gravity. So all we did here is replaced the normal force with Fg cosine theta, or the vertical component of gravity.
And we did that so we can rewrite it in terms of variables that we know, that we can plug in later.
So if I can write equals mg sine theta minus Fg, force of gravity, is equal to mg, remember? Mg cosine theta times mu over mass. This is my equation for the horizontal acceleration, or acceleration down the plane. The cool thing is that every single term has mass in it. What does that mean? I can totally cancel out the mass. I don't care about the mass. I don't need the mass. So in reality, this doesn't have to be a box of Lucky Charms. It could be a brick, it could be a pencil box, it could be a calculator, anything sliding down the plane, regardless of the mass, because the mass doesn't matter.
And they would all have the same acceleration.
Alright, so this is my end result for the equation. I don't have any zeros to plug in, so I can go ahead and plug in my numbers. I'm going to use 10 as g to make it simpler. Alright, and if I plug that into a calculator, I get 2.4, and the units are meters per second squared because this is an acceleration. And so notice, now that we've added friction in, the acceleration is much less than it was when we didn't have friction, because friction is opposing that motion, so the acceleration becomes less.
Does the number that we got make sense? Well, we got a positive number for the acceleration, which makes sense because the block is speeding up or accelerating in the direction of the positive x-axis.
Alright, let's accelerate into the next part of the problem. Since we're starting a new part of the problem, we start from step number 1 in our problem solving method. First step is draw a picture. We already have a nice picture. We don't need to draw it again. In terms of labeling our knowns, we have everything labeled except we have one more known to add on to this, and that is the acceleration that we found in part A of the problem. So now our acceleration is not a question mark. Our acceleration, as we found earlier, is actually equal to 2.4 meters per second squared. And so we can actually use that now. All right, what is our target? Part B is asking us to find the speed of the cereal box when it gets to the bottom. So our target is v final in the x direction. That is our question mark. All right, now let's look for an equation. Our equation has to have the final velocity in it. So I see an acceleration, I see a starting velocity that's 0, I see a final velocity, and I see this x, or a displacement essentially, and so I'm starting to think kinematics. So if you go to your equation sheet, for kinematics we use the first 3 equations, and off the bat, I know I can't use the top 2 equations because they both have time in them. We don't know anything about time, so I'm going to have to use the third equation. If you look at the third equation, it has a final speed in it, a starting speed, an acceleration, and a displacement. And we have all of those variables except the final speed, which is what we're looking for. So that sounds like a good plan to me. All right, so for part B, our equation, the third one, is the v final squared equals v naught squared plus 2a delta x, or our displacement. I guess I could have called this length of the inclined plane delta x,
because it's the amount that the block was displaced from start to finish.
So I have an equation. My next step is to plug in my zeros, and that is our starting velocity because the box starts from rest. So now I rewrite it, and I'm good to go to plug in my numbers. I need to isolate the variable, and it looks isolated but not quite because it's squared. We don't want the speed squared, we need the speed by itself. So I'm going to have to square root both sides, and I get that the v final in the x direction, or along the incline, is root 2ax delta x. Don't let that delta x scare you. All that means is a change in position. And for this box, the changes in position is from start to finish. It travels the entire length of the incline. So that is our displacement. That's our change in position. So I get the root. I'm rooting for you. You've got this. So I'm plugging in my numbers. 2.4 times 1.5. And if you plug that into your calculator, you get 2.6 meters per second because it's a speed. So my next step is to ask, is this reasonable?
The speed is positive.
Because it's moving along our positive x-axis. That makes sense. 2.6 meters per second is a reasonable number. It's not like 3 million. If you got 3 million, I would recheck your work. That looks good to me. I'm going to present my answer that the v final in the x direction is equal to 2.6 meters per second. And I'm going to box it to make it easy to find. And there you go.